Okay, let's get started. Thank you. So today is definitions and examples. I will try to make it interesting. It will take a superhuman effort to make definitions and examples not just totally dry and boring. So you'll let me know at the end of the lecture if I'm superhuman or just a mere mortal, okay? So we're doing abstract linear algebra. When we're done with this, if you understand what are scalars, that the word vector is actually overloaded, just like an overloaded function. If you understand what is a linear combination and how to use that to check whether vectors are linearly independent or dependent, then you're in pretty good shape. Because once those concepts are there, then bases and everything else is done, span, all the harder stuff comes. So these are really the fundamental things, and we'll get them done this week. Okay, so there's no review because we're starting something brand new. Let me put this back. Okay, so I'm going to define something called a field, and what I want you to have is an example in mind. Okay? The real numbers is the canonical example. So we're going to define abstract objects. Now, what happens with the mathematicians is everybody knows how to work with the real numbers. And then somebody proves a theorem based upon properties of the real numbers. And then these things called complex numbers, for example, are created. And somebody goes and proves a theorem about complex numbers following exactly the same steps as the guy or gal who proved the thing about the real numbers. And then somebody else comes along and defines another set of objects that satisfies all of the properties of the real numbers, and somebody else proves this other theorem following all the same steps. And then finally somebody says, time out, all of these things are the same, and we're going to give them a name. You put all these properties together, and then you do the proofs once using that property, okay? So that's why this level of abstraction. It allows you to cover many examples. So a field is a set of elements, script F, of elements called scalars. So scalars are elements of a field, and they have two different operations added on them. One is called addition, it has a plus sign. And one is multiplication, and they're showing it with a dot, just to show that when you put alpha and b together, if you don't put a dot, we know it's there, it's alpha times b if it's not a plus, okay? So they're using the dot for multiplication. And so think about the reals when we go through this, and make sure that all of this stuff makes sense. So for every pair of scalars, I need to be able to define their sum and their product. And the sum we call alpha plus beta, and the product we call alpha times beta. And then often we just leave out the dot, okay? So I'll typically just leave out the dot. Now, these operations, once they're defined, they have to satisfy that they are commutative. It doesn't matter what order you add things, nor doesn't matter what order you multiply them. Sound good? 3 times 7 equals 7 times 3. We're good with that, okay? You have associative rules. So if you have 3 of them, you can add up the first 2, then the third one, or you can add up the last 2 and then add it to the first one, okay? All of these things are properties that you are very comfortable with the real numbers. Whoops, I didn't want that to happen. Come on, I just want to do this. Okay, and then you have distributive rules. You take alpha times the sum, use the same thing as if you multiply alpha and beta, you multiply alpha and gamma, and you add them up. Those are all things we're very comfortable with the real numbers. Final things, we need to have a 0 element, and it has the property that you take any element of the field and you add 0 to it. You don't change the element. And it has a unit, a multiplicative unit. It has the property that you take any scalar, you multiply it by the unit, and you get the scalar back. And then there's these last 2. Every scalar in the field has an additive inverse. For every alpha, there is a beta such that I add it to alpha, I get 0. We always call beta equal to minus alpha, okay? It's an additive inverse. And then, if you have an element of the field, so a scalar, and it's not equal to the 0 element, it has a multiplicative inverse. So there's another element in the field such that when you multiply alpha and times that element gamma, you get the unit back, 1. Okay, so those are the definitions of a field. Get down there, okay? Okay, so to show something is a field, you must check all 7 axioms. Okay? Super boring. To show something is not a field, you only need to show that one of the axioms fails. Okay, it's super obvious maybe what I've written down, but it just to be clear. So why on an exam would I never have you check that something is a field? It takes too long, okay? Why on an exam might I have you check or have it true false if something is a field or not? Because it's really easy to show it's not. You just find one, okay? So that's an important thing to note. Now let's do some examples. And we do some non-examples. Okay, so when I try to understand a definition, I try to understand sets or objects that satisfy the definition, the axioms, and those that don't. So example, counterexample. So So real numbers. I said the real numbers was the canonical thing. It's based upon that. The complex numbers as well, though. They satisfy all of those axioms. Okay? We just do the addition on the real parts and the imaginary parts, okay? So there's no problem. We use our general rules of complex numbers, okay? Another set, the rational numbers. Okay, remember these are rational numbers. Okay, so we could go through and check every single one of the axioms, but we won't, okay? You can go through at home and just have your friend pick a random number between 1 and 7 and you check it, okay? And if that works, you're good. Non-examples. Okay, A. The integers. Okay, remember the integers? 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, etc. Okay? Okay, do I know how to define addition and multiplication of integers? No problem, right? Does it matter in which order I add my integers or I multiply them? No problem, right? Does it matter in which order I associate? No. The distributive rule, all that stuff works? Darn, okay. Hey, maybe they're a field, right? Do I have a 0 and a 1? Looking good, right? See how boring it is to check them all? Oh, okay, so now to every element in the field, there has to be something. Does that work? Yes. What about 7? Yeah. What's the multiplicative inverse of 2? It's a half, we think, but there is no element in the integers such that I can form this. That's okay. I don't really say half is not an integer, but there's no integer. Okay, so it fails 7. What if I did the natural numbers? Remember, they start the counting numbers, 1, 2, 3, 4, 5. No, this works, this works, this works. There's no 0, okay? So fails 5 and it fails a whole bunch of things, okay, but it fails 5. Fails more, okay? Whoops. I think numbers 6 and 7 as well. Let's see, what is, yep, so they fail 6. What number can I add to 2? What natural number can I add to 2 and get 0? Okay, so it fails 5, 6, and then there's no 7 either. So it fails 5, 6, 7. But I only needed to show one of those. Only needed to show one. Okay. What about A equals 2 by 2 real matrix? Inverses Yep, units may not exist. Okay, anything else? The commutativity, A times B is not necessarily equal to B times A. Okay, so this is not true for all 2 by 2 matrices. So that they cannot form a field, at least under our usual notions of how you multiply matrices, okay? So fails, and what was that number? That was 3? 2. Oh, that was bad. Fails, number 2, and others. Get my red back in there. Yeah. Okay. Okay, so for us, R and C, the real numbers and the complex numbers, will be our main fields. We will do some examples using the rational numbers just to make us think. Okay, so if you're good with the reals and the complexes as fields, adopt that new name, then we've got that part down. Questions? Please.
That example C.
Mm-hmm.
Even if the conditions were satisfied, we could call a 2 by 2 matrix a scalar.
You're getting at a really important point. If it were true that the 2 by 2 matrices satisfied axioms 1 through 7, we would call them scalars. Now, it is false that the 2 by 2 matrices satisfy axioms 1 through 7, hence we do not call them scalars, but you're absolutely right. If they did, we would call them scalars. The complex numbers are scalars. The real numbers are scalars. Excellent.
So integers are non-scalars? How do we refer to them?
They're integers.
Okay.
Yeah, so the elements of the field are called scalars. Okay, now I want to define vectors. Okay. Now I want you to have the following example in mind. So let A and B be 2 by 3 real matrices. Why 2 by 3? Make them 7 by 11 if you want. Make them 9 by 12. I don't care. Okay? Just that they're not 1 by 1. That's all I really care. Okay? Now, I'm going to write something down. How should we define the addition of these two matrices? Well, we want to define it such that if I look at the ij element, the ith row and the jth column, the same notation we're using in homework, that is equal to, by definition, aij plus bij, right? Well, I should really write it like this to be just like, let me rewrite it more smoothly, and then you'll be able to write it down, plus, then I do the ij element of b. Why am I making a big deal about this? The aij element of A is a scalar, it's a real number. The ij element of B is a real number, and you guys know what the plus sign means for real numbers. What do I have here? I have a different object. I have a 2x3 matrix. I put the same sign there, okay? But what that sign means here is I just add the corresponding entries. You've done that for so many times that you don't even think about it, okay? But what I'm trying to get clear is the symbol here and the symbol here, they're the same, but they don't mean the same thing. This means addition of real numbers, and this is addition in the set of 2x3 matrices, where I add the corresponding entries. Okay, now, so you guys are used to this meaning definition. Let me give you a little bit more sophisticated notion of that. X, by definition, equals to y means y is already understood and I am defining the symbol X, okay? So I'm just trying to give a direction to when you have something is by definition. And so you guys have seen this a lot of times for equals by definition, but are you defining the left-hand side or are you defining the right-hand side? Meaning, are you supposed to already know what this means and hence this is telling you what this means? Or you already know what this means and you're defining what this means here? So for this, I would prefer to write it like this. A plus B, ij is by definition equal to A ij plus B ij. And the nice thing is I can move this to the other side. I don't do it very often, but it would still be fine because I know okay, so whichever side has the dots, that's the one that's being defined. Now, don't worry about it. I will almost, no, I think 99% of the time I put it on the left, okay? So the left is on the right, so. Okay. So let's go back to this notion of addition, and here I'm making a sense that this is addition of matrices, but this is something I know it's the addition of real numbers. And then if I want to define alpha in R, then the product of alpha times that matrix, the ij entry, is simply alpha times the ij entry of aij, okay? Here's a scalar times a matrix. I'm telling you what that product means by here's a real number, and we know how to multiply them. Abstract? Yes. Precise? For sure, okay? So, this is the example I want you to have in mind because we're going to define vectors. And for some of you, you're not going to like it. Vector space. Axioms. Bingo. Okay. Another example I want you to have in mind is just R2, column vectors with 2 entries, okay? So we call that R2. We have a X and a Y, for example, stacked up on each other. Okay. And then instead of calling this a linear space, we're going to call it a vector space. Okay, so after that butchering of wonderful, beautiful handwriting. Okay, so a vector space needs 2 objects. It first needs a field, so think reals, think complexes, think rational numbers. And then it needs another set, X, script X here. And the elements of that set are called vectors. That's why I'm calling it a vector space instead of a linear space, because the elements are not linear things, they're vectors, okay? Now, it has 10 axioms here, and we have to have 2 operations defined, vector addition, okay? And then scalar times vector multiplication is how I usually write that. Like say scalar multiplication, but for me it's even more clear if you say scalar times vector multiplication. Now, let's start looking at the axioms. Get them down where I don't have to reach so high. We're just looking at the vectors. We need to have a way of adding them. That's called the vector sum. Yeah. When you add one vector to another, it can't matter the order. So vector addition has to be commutative. It also satisfies the associative property. Okay? So let's just stop here 1 second and go back to our little lowly 2x3 matrices, okay? Do I know how to add 2x3 matrices? Yes, here's a definition of how to add 2x3 matrices, okay? So does it matter in which order I add my 2x3 matrices? Is A plus B equal to B plus A? And why is A plus B equal to B plus A? It's true because for real numbers that doesn't matter, okay? That's how I prove that the addition of 2x3 matrices satisfies the commutation, is because it's for real numbers. It's inherited from the real numbers. Okay, And for my 2 by 3 matrices, if I have A, B, and C, can I add up A and B, then C, and get the same thing as if I take A and then add it to B and C? Looking good, right? Okay. My addition has to have a 0 element called the 0 vector. Do I have a 0 vector for 2 by 3 matrices? All zeros, okay? I have to have an additive inverse. For 2 by 3 matrices, do I have an additive inverse? No problem. You guys are following through, okay? Now, this is telling me how my scalars interact with the vectors, okay? So this is the scalar times vector product. Okay, they're calling it the scalar product. I call it scalar times vector multiplication. Do I know how to take a real number as the scalar and multiply it by a 2 by 3 matrix? Yes, I wrote that down. The ij element is, etc. Now, when I do that, if I have two scalars, like 3 times 7 times my matrix, is that the same thing as doing 3 times 7 and getting 21 times the matrix? It works, huh? Then I need, let's see, I need the scalar multiplication. I need the scalar multiplication to be distributive. A and B times 4 is the same thing as 4 times A plus 4 times B. Scalar multiplication is distributive. 4 plus pi times A is equal to 4 times A plus pi times A. No problem. And for any vector x in here, if I take the unit scalar times the vector, I get the vector back. So I take 1 times my matrix, I get my matrix back. What did we just learn? 2 by 3 matrices are vectors, so matrices are vectors. Okay? That is, you have to get that into your head. Matrices satisfy all the properties of being vectors, okay? So, let's do examples. Question, please. Yes.
Do we really need number 7? Because it's a scalar, does that mean it's already satisfying? That alpha beta could already be written as a single scalar in the...
I'm pretty sure this is the minimal set, but I've never tried to see if I could use 1 through 6 and 8 to 9 plus the definition of the 7 axioms for a field to deduce this. I've never checked. I'm pretty sure, but I'm not 100% sure. I'm only 99.47% sure, okay? Okay, so let's give examples of vector spaces. Vector spaces. So I need the set of vectors and I need the field. These are vectors and this is the field. Okay. Every field forms a vector space over itself. What that means is I take the vectors as the scalars. So I put the same thing here. So if I have real numbers and real numbers, the real numbers being treated as vectors, I know how to add my real numbers. I know how to do scalar times vector multiplication. That's all just properties of. Okay, so that means the real numbers as vectors and the real numbers as scalars forms a vector space. The complex numbers as the vectors and as the field. The rational numbers as vectors and as the field. It's all fine. And it all works because everything you need is baked into the axioms of a field. You know how to add elements of the field, you know how to multiply them, and you use those definitions for the vectors and everything works. So it's abstract, but it's true. Okay. Remember, the first thing is the vectors. I'm going to take my vectors to be complex numbers. I'm going to take my scalars to be real numbers. Okay? Do I know how to do vector addition in the complexes? Yes, I use the same definition of how I add complex numbers as a field. It's the same definition. Do I know how to do scalar times vector multiplication? Can I take 7 and multiply it by 4 plus 6j? No problemo, okay? And I get a vector, okay? So this forms a vector space. Let's do quickly a non-example, then we'll do some more. Okay. I take my vectors to be the real numbers, and I take my scalars to be the complex numbers. Do I know how to do vector addition? Yes. Okay. Now, with the normal rules of scalar complex numbers multiplying real numbers, can I define an operation on scalars times vectors and get vectors back? You see the problem? J times 1 is not a real number. Okay? So the order matters. These are the vectors. 4 alpha plus beta j times gamma is gamma alpha plus gamma beta with a j. Okay? Here the problem is the usual definition of multiplication of complex numbers times reals does not give a real number. Is there possibly some bizarre notion of multiplication where you can make it work? I don't know, okay, and I don't care, okay? So this is a non-example under the usual rules of multiplication of complex numbers. Okay? It is not a vector space. Not a vector space. Are we good with that? The problem, okay, so let's do another example. So examples continued. Give myself a little more space. Okay. Let me go back and refresh something I did here, because I'm going to do it in a little bit more general context. I knew how to add real numbers, and I extended my plus sign to a bigger set of objects, 2 by 3 matrices, by just doing component by component addition, okay? And I did the same thing for multiplication. I know how to multiply two real numbers, and based upon that, I told you how to multiply a real number times a matrix. Okay, so here's my example. I hope you like it. Field is the reals. I'm going to let D be a subset of the real numbers. So it could be something like this. A infinity, etc. I don't care. It could consist of just 3 elements of the real numbers. It's just a subset of the reals. I don't care. Okay? And I'm going to define X and try to turn it into a vector space. It's the set of functions that map D to R. So real valued functions from D to R, okay? People remember what a function is? It's a rule that takes elements in the first set and maps them to or creates elements in the second set. So for every point in here, f evaluated to that point is a real number. Okay? For every x, I'm going to use t, so let me do that. F of t is a real number. That's what we mean by f takes d to r, okay? Every point in t, I have a rule that associates, and f is that rule that associates with that t a real number. Okay, the reason I want to do that is I'm going to now define vector addition on my functions. Okay, so I will define vector addition and scalar times vector multiplication by okay, I believe you guys know how to add sine of x to e to the x and stuff like that. I totally get it, okay? But what I want to do it is more fundamentally saying, I only believe you know how to add two real numbers. I only believe you know how to multiply two real numbers, and then take that definition and extend it to this broader set, just like we did with matrices, where I broke it down to ij element by definition equal to. So that's how I'm going to do it. Okay, by A. For every two functions in my set of functions, I define their sum by, for every t an element of D, f plus g evaluated at t is by definition equal to f of t plus g of t. What have I done? I've taken two rules. F functions are rules that map from the domain to the codomain. I've shown you how you add two of those functions by giving you the rule that tells you how the addition takes elements of the domain and goes into the codomain. Because this is a real number and this is a real number, and that's the plus sign you guys understand. And now I've extended the plus sign to functions, just like I did for matrices, by breaking it down to the addition of real numbers. Trying to make something super dry, super interesting. How am I doing? Is it pretty cool? Okay, front row's cool. Anybody in the back kind of digging this? That's why we sit in the back, okay? No, just kidding. Trying to have a moment of levity, okay? It's hard when you're doing math. So now I need to define scalar times vector multiplication, okay? So I take, for every vector in my set, for every scalar in my set, I define scalar times vector multiplication by, for every t in D, alpha times f evaluated at t is by definition equal to, I think now you guys get it. Okay? It's the product of real numbers. We know what this multiplication sign means because f of t is a real, alpha is a real, and that's the product of real numbers. And now I've told you what is the product of a function by this, okay? So fact, xf is a vector space. Okay, so just like 2 by 3 matrices with real entries is a vector space over the real numbers, real valued functions form a vector space over the reals as well. Okay? So, real numbers are vectors, complex numbers are vectors, rational numbers are vectors. Okay? Cool. 2 by 3 matrices are vectors, and functions are vectors. You getting it now? There's this whole class of objects that satisfy all of the axioms we need to be vectors. So when I teach you how to manipulate vectors, and I teach you how to do minimum distance problems, how to best approximate one vector from measurements with respect to another class of vectors that you're using as estimators and get best estimates, we don't care if they're columns of numbers, they're matrices, we're fitting functions to them, as long as we're using just the rules of a vector space, we solve all of these problems at the same time. That's why we do this abstract nonsense, okay? We do the abstraction so that we solve whole classes of problems at one time. That's what Rob 501 is about, getting your minds around that concept. So that when you see new problems in practice, you bring them back to something and do concrete calculations. There's a question? Okay, this one first.
Are there limitations on the functions, like they have to be defined over the whole set?
Nope. D can be any subset of the reals. It can consist of one point. I never used the fact that D had 11 elements, a continuum, but these are just common examples when we do them. I'll get one. Suppose I had a set that had 5 elements in it. Okay? Then functions and columns of 5 numbers, they're the same thing. In MATLAB, when you define a function numerically, you say t equals, and you go the beginning point, you go the delta t, you go the ending point, and then you write sine of t, and you think you're manipulating sine of t, but you're really manipulating a vector, maybe you had 1,000 points in it, that has sine of the first point, sine of the second point. In MATLAB, vectors and functions are the same thing too when you do numerical calculations, okay? You just never thought about it. There's a question over here.
So if we go back to the example of vector space, the complex number, the real number is the scalars of the real numbers are a subset of the complex number, right?
Mm-hmm.
So if we have like for
This-
every two field A and B, if B scalars are a subset of A scalar, is it true for every A and B that A comma B is a vector space?
I think that would work, yeah. I'm not going to repeat the question because I don't want to confuse people, but I think that works, yeah. Yes, you can take the reals as the vectors, and you can take the rational numbers as the field, and everything works, because a rational number times a real vector is a real vector. But if you flipped it, I take a real number, like pi, times a rational number. That is not a rational number. That cannot be vector. Question?
So, is every field can also be a vector space?
Yes, so every field, if I use the rules of multiplication and addition from the field on the vectors, then that works. Vector and field being the same always works. And so these are the common ones that we would do.
So does that mean that every element of the field is a scalar and vector?
Yes? But you have to decide how you're looking at it. It's sort of like light. Is it a wave or a particle? Yes. Okay? It's both. Which one do I use? Depends on the problem I'm trying to solve. Okay? And we do the same thing with here. Cool. Okay, I think you guys are starting to get your head wrapped around it. So now, how do I prove that XF, these functions over the reals, is a vector space? How do I do it? I check all 10 of the axioms, okay? Notice I'm going to put U check. Of the axioms. Boring, okay. So, well, let's just check one of them, okay? Let's check number 8. Let's go back and see what number 8 is, and why I want to do that one. So let me just show you how you would check that a scalar times the sum of two functions is the same thing as the scalar times the first function plus the scalar times the second function, okay? Let's just check that one as an example, okay? So. Okay, so we want to show, and I've got better notation in these notes over here. Okay, so for every alpha in our field, which is the real numbers, and for every f and g in X, we want to show that alpha times f plus g equals alpha f plus alpha g. Sorry that I crammed that in there, okay? Take an arbitrary scalar, we take two functions, I want to show the distributive rule for multiplication. Method. Show left hand side equals right hand side. So it's simply going to be a applying the definitions. Okay, so let T be an element of D, and let's see if this rule and this rule give the same real numbers. Do those functions give the same real numbers? Okay? Why did I write this like this? This is my value, and this is the function evaluated at that point. What is its definition? Okay, it's alpha times f plus g evaluated at t. Because that's how I defined a scalar multiplying a function. I take the scalar and I multiply it times the function evaluated at that point. This is supposed to be a real number because I know how to do addition of functions. Okay? And this, by definition, is equal to alpha times f of t plus g of t. And now everything is a real number, so that equals alpha f of t plus alpha g of t. So this function at a point is this sum of real numbers, and then a scalar times real numbers, that's the distributive rule or whatever. So that's the left-hand side. Okay. What's the right-hand side? So I've got alpha f plus alpha g of t is by definition equal to what? This is a function. This is a function. I evaluate them at a point. I said it was this function at t plus this function at t. Function plus function. What is this function at t? Okay? And that's the right-hand side. Okay? Right-hand side equals left-hand side. Check. So that's how we do axiomate. It's super boring, okay? But it's just taking the definitions of what the symbols are and writing it out. The same thing you would do in computer code. You're trying to simplify something or just like computer code. How we feeling? Symbols are going like this, or they're going like this, or are they going like this, okay? No, they're all fixed just perfectly in my brain. They're all that. Okay. No? Okay, more vector spaces. Let F be a field. Define F to power n to be the set of n tuples. Tuples of elements of F n tuples, n tuples, people say the same. So this just means alpha 1, alpha 2, alpha n, such that for 1 less than I, less than n, alpha I is in F. Okay? Guess what I want the n tuple to be? We're doing examples of vector spaces, so I want it to be a vector, okay? I want this to be a vector space, and I'm going to use the field to be F, because I know how to add these things, etc. So, just to do this again and again so that it becomes second nature, define vector addition by, here's one n tuple, here's another n tuple, and I'm going to define the overloaded notation of plus by, anybody have an idea? Element-wise, yay! Yeah, okay. So it's alpha 1 plus beta 1 dot 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 alpha n plus beta n. Okay? Let you catch up. I just want to keep getting this in. Level of precision, abstraction. We know what this plus sign means because probably they're real numbers or complex numbers when we're doing our actual calculations, okay? So we know what this plus sign means, and you guys have known for a long time what it means, but now I've really formally defined this. Okay, I'm going to do the scalar times vector multiplication. You're going to get it, but let me ask you something. Does it bug you that the same symbol's being used for 100 different things? Yes? No?
The alternative is you have a programming language. You have different names for each function. Add matrix or add vector or add scalar.
Yeah, the alternative is I would need a different symbol for every time I'm adding different sets. Okay? So I'd have an add with a little mat on here, an add with a little fun on here, an add with, just drive you nuts, wouldn't it? So you just get used to it, overloaded, okay? So that's how we do it. That's the only way you can survive is to say this symbol, I interpret it in the context, live with it, okay? Just a little moment of levity once again, okay? Okay, so now define vector addition by this and scalar times vector multiplication. We multiply scalars times vectors, not the other way around. Scalar times vector. Scalar times vector multiplication. Get it in. By alpha times beta 1 beta n by definition equal to, and there's no surprises. Conclusion, Fn F is a vector space. Okay. So n tuples with the obvious rules become a vector space, and I don't have to say it. I put R in here, I get RnR. I put C in here, I get complex numbers. rational numbers, any field you want to put in there. Okay. The last one, matrices. Instead of n tuples, f n times m is equal to the set of all A equals n by m matrix with entries in the field. I'm going to spare you the gory details because I think you get it now. If I want these to be vectors, how should I define vector addition? Element-wise. How should I define scalar times vector multiplication? Element-wise. And then it becomes a vector space, okay? So f n by m f is a vector space with the obvious rules of vector addition and scalar times vector multiplication. Okay, I will not write them down. I will not write down those rules because you know them, okay? I don't have to do it. We've done enough examples like that where you get it, okay? So we have a ton of vector spaces, okay? So we can build vector spaces out of just columns of real numbers. We could do rows of real numbers. We do matrices of real numbers. We do matrices of complex numbers. We do functions from some subset into the real numbers. We build vector spaces. So we have tons of vector spaces. Tons and tons and tons of vector spaces. To check a vector space, 10 axioms. To check a field, 7 axioms. We will almost never check all 10 or all 7. Question at the back there.
This process is just showing the 2 of the 10 axioms.
Well, this is just saying when I define my vectors and scalars, I need to have 2 operations. I need to have vector addition and scalar times vector multiplication that satisfy, and then I put axioms 1 through 10 here. Yep. And just like we did with functions, we checked 1. It'd be exactly the same operations to check here. And it will be just the same as when I had you at the very beginning. I was trying to prime the pump to say matrices are vectors. Scalars are vectors. Because that's R1, R1, okay? R1, R. N tuples, 1 tuples, okay? That's the vector. And then the real numbers, okay? So the term vector is extremely overloaded. Almost everything you know can be made into vectors. Okay, cool. A little more power left in you. We've got 10 more minutes. Let's talk about subsets for, change gears. We're going to move towards defining subspaces. Okay, what is the notation? A contained in B means for A and be two sets. Okay, the only thing I'm clarifying here is that some of you, maybe only 2 or 3, but probably 10, want A to be strictly smaller than B if it's a subset, okay? And that is completely false, okay? All this notation means A is contained in B if and only if for every element A and element of B, it's if A, we also have that A is an element of B, okay? So the reals are a subset of the reals. It's okay. It's the whole thing. Now, what does it mean that two sets are equal? You got it. A is contained in B, and B is contained in A. So you have two descriptions of something. One is called A, and the other one B, and you want to assert that they're equal. You show that everything in A satisfies all the hypotheses of B, and everything in B satisfies all the hypotheses of A. Okay? I know it seems obvious, but I'm just making it clear. Yeah, 1 second. We have no notation like A strictly contained in B in Rob 501, okay? Yeah, we're not doing that, okay? We don't mean that there's at least one element in B that is not in A when we do that, okay? We don't do that. We don't do that. A contains in B means every element of A is in B, and they could be the same. I don't care. Question, I heard a question. Yes?
Wasn't there some symbol like sideways where there's an underline?
Yeah, so we're not doing that. Yeah. This is the subset sign, and A is a subset of B if every element of A is also an element of B. That's all we mean. We're not doing any of that other fancy notation, okay? Some of you have seen it, and it messes you up when you do other things in class. That's all I'm making I'm saving somebody some grief. That's all. Maybe not you, maybe not you, maybe you. I don't know. I'm saving me grief, okay? That's for sure. Yeah. So I'm going to leave you with this definition, subspaces, and we'll untangle it probably on Thursday. So definition. Let XF be a vector space. Okay, so, comma. Okay, these are the vectors, these are the scalars. We have vector addition, scalar times vector multiplication, axioms 1 through 10. And let Y be a subset of X. Once again, it could be all of X, it could be part of X, I just don't care, okay? Then YF is a, excuse me, I don't want to write it like this. So I'm going to mess up my notes just like yours are. I apologize. I got ahead of myself. Then Y is a subspace of X if YF is a vector space when you use the rules of vector addition and scalar times vector multiplication inherited from the bigger vector space. Okay, let's write this down. We'll talk about it. And then we'll pick up here Thursday. So all it is saying is that when you add vectors in y, look, anything that's in y, it's also in x. So how do you add the two elements in y? You use the same rules that you would do in x. You can't define another way to do it. Okay? Then it's not a subspace. It could still be a vector space, but it's not a subspace of x. To be a subspace of x, when you add the things in y, they have to be the same way you would add them as in x, because if it's in y, it's in x, so I know how to add them. And if it's in y and it's in the field, I know how to multiply them because I know how to do multiplication in x. That's what it means. You just can't change the rules. You have to play by the same rules. That's all the definition says. It's a subset. You play by the same rules that you have in the bigger vector space, then this becomes a vector space. That's a subspace. And this is not a vector. This is a graduate student instructor who's smarter than me by exactly the proportion of our heights, okay? So he's a lot smarter than me. He's younger, but he is your graduate student instructor. He's been Nils. He's been answering some of your questions on Piazza and things like that. And he'll be running the...
Yeah, so we'll have a recitation section this afternoon as well as tomorrow afternoon, I guess evening, 6 p.m. So yeah, feel free to stop by. We're going to run through some problems covering stuff that you should know coming into the class. So some of the background material that we're asking for in the first assignment. We'll kind of go over that in a little bit more depth this afternoon. So,
What room is that again?
off the top of my head, I don't know, but it's on the canvas. Yeah.
Yep, so SRB something.
Yeah.
Everybody know where the Space Research Building is? It's just north of Aerospace. It has a nice new front on it, and it's right next to the drone netted area. So it's just west of that. Okay, we're done. Thank you. Hey, no,
Sorry, I couldn't stop by earlier.
no, it's fine.
Yeah, I was just in a meeting.
No.